for coming to the learning machine, not machine learning seminar, learning machine seminar. Really great to have Phebe Vayanos here from USC. Phebe is in does operations stuff there, but is has a whole bunch of really interesting work across machine learning, optimization, applications to social services. Associate Director of the Center for AI in Society. Long list of awards that I'm not going to name here, but I think we're suffice to say we're really lucky to have her.
Thank you so much, Nikhil, and thank you for inviting me. Thanks, everyone, for being here. I'm very excited to be able to share some of our work. This is probably the second time I'm presenting this, so quite fresh work, I would say. So I'm Phebe. I've been with USC for about 7 years. I just got tenure. I'm associate professor now. I've been associate director of the Center for AI in Society at USC for since its inception, basically back in 2016. This center is basically a joint initiative between the schools of social work and engineering at USC. So basically what we do is basically conduct research in operations research and AI to solve important societal problems. So some of the things I've worked on relate to homelessness, relate to substance use, suicide prevention. So just to give you a little bit of a flavor of the problems I'm interested in. And in general, I look at the problems from a kind of equity lens, and this is what we'll be doing today. So in particular, I'm going to be sharing some of our work today in collaboration with LASA, the Los Angeles Homeless Services Authority. And in particular, we're going to be talking about how we're helping them design better policies for matching people experiencing homelessness to very scarce housing resources of different types. There's going to be two parts, hopefully, in my talk, if I make it to the end. The first part is, and my clicker just died. The first part is joined with, is led by my PhD student, Bill Tang, and the second part is joined with, is led by Nathan Joe and Bill Tang. And Nikhil was telling me he was trying to hire Nathan. Nathan was an undergrad in my group and then went on to Stanford for a research assistantship. In the first part of my talk, I'm really going to be focused on the problem of, okay, given a certain objective that the policymakers are interested in optimizing and perhaps some fairness constraints, how do you go about from the data to design a policy that's going to align with what they're looking for? And in the second part, we're going to look more at like an ethical perspective, like, oh, how do you go about deciding what fairness requirements you're going to be setting in a system? This has been a huge pain point from our collaborators' perspective in that, you know, you often want many different types of fairness and like, is it even possible to get them all? So this is the kind of stuff I'm going to be talking about today. Let's see if this works now, maybe. Yeah, okay, good. Okay, let me not bore you with the outline, but basically this first part, these first 4 sections are really going to be about the policy design part. And then this part down here is going to be about these impossibility results in terms of the different fairness metrics one may want to have in the system. So let me start with a little bit of a motivation. Well, homelessness in LA, like in many US cities, is a really big issue. Just to give you a bit of a sense of the scarcity of resources, as of the point in time count in 2022, we have over 69,000 people experiencing homelessness. At the same time, there only exists about 28,000 permanent housing units. I'm going to focus for this talk on permanent housing allocation. And, you know, be careful. This does not mean that at any point in time I have 28,000. This is my entire inventory, right? And like some units may become available over time. So I said I'm going to focus on permanent housing allocation. There's really 2 types of permanent housing. One is what is called permanent supportive housing, or what I will call PSH for short, which is a long-term housing intervention that also provides support services. The second time of permanent housing is what is called rapid rehousing. This is a shorter term. Hello, Omar. This is a shorter term voucher-based intervention. I'm going to be calling this RRH for short. And for the purposes of this talk, I'm gonna be allowing people to receiving what we call services only, which means they do not receive a housing resource. They just receive support services. Think about this as mental health services, substance use services, and so on. So now how has a housing allocation worked in LA? The main information that's used to match people to resources is what is called the VISP data, or Vulnerability Index and Service Prioritization Decision Assistance Tool. Very short name. This is basically a vulnerability score-based allocation. So when someone enters the system, they answer a survey. I have like the first 3 questions of the survey here on the right. They ask quite personal questions related to housing and homelessness, current living situation, history of substance use, and so on. And depending now on how you answer each question, you get a score. And all these scores are then added up together to form your vulnerability score, which is meant to be a predictor of how vulnerable you are. Basically, take it loosely speaking as meaning, you know, what is the likelihood that perhaps bad events are going to happen to you if you remain on the street. It's basically aimed to predict your outcome under no treatment. That said, this is not a data-driven score. It was created by social scientists with, you know, who have kind of expertise in what may lead to adverse outcomes. Yes.
Do they know that the score is being used to give them these results?
Good. It's publicly available. It's public information, but I don't know per se. It is shared. It is meant to be shared with them. I think where you're getting at is a question of strategy. The reality is, like, from all our communications with LASA and with matchers at LASA, with matchers outside of LASA, with our community advisory board, that people are not strategic about it. For one thing, you can somewhat verify a lot of this information because it's not about preferences, right? It's about like things that have happened to you. But also, if anything, people shy away from revealing information that would lead to a higher vulnerability score just because it's highly private. Like, some of these questions are, you know, I cannot imagine like revealing this if I were in that position. So now, how is this vulnerability score? Yeah.
Sorry, can I ask a little
yeah, of course.
And is this information like forwarded to like other agencies for like other sorts of decisions, or is it?
I don't think so. I don't think so.
Also, like, empirically, when you look at the data, do you see any bunching in the distribution?
Yeah, it's kind of Gaussian to some extent. Yeah. Yes.
Is this, what period does this pull at? Is it just when they come in, or is it asked again?
Good. It may be asked again, or it may be asked if the information you see in the survey does not look representative of what you see. So, for example, maybe there was a data entry error or something like that. You may have to retake the survey. Yeah. There's plenty of interesting questions to discuss about this, but let's save them for the end. Like, honestly, there's a lot of interesting questions. So now, how is this in principle used for matching? Well, the idea is that the more vulnerable you are, the more you should be directed towards more supportive resources. So the idea is that the people who score in the top bucket should be directed towards permanent supportive housing. People who score kind of in the middle range get rapid rehousing, and then those who score low receive services only. There's a few issues with so there's some nice things about this. The first thing is that it's very interpretable, right? And it's nice to prioritize those who are the more vulnerable, right? So these are some very good things about it. On the other hand, you know, currently at least the vulnerability score is not tied to a particular outcome, right? It's not driven by data, and there's not a particular definition of outcome that it's trying to predict. And the second thing is, similarly, the actual policy is not tied to a particular outcome. Perhaps, you know, if some of the people that score very high were matched to RRH, they could have a good chance of exiting homelessness if that was the outcome you're tracking. And so you could give them some RRH instead of PSH. So the policy as well is not tied to outcomes. And in addition, it's not tied to resource capacity. So these thresholds, as they're set, they are not, they don't match the capacities for that resource. And in practice, actually, you know, this a score is not, this policy is not actually implemented as is. Instead, it's used as a guideline, right, that matchers use, and it's basically an input to guide the matching process or to identify certain individuals that may be in particular need of housing and so on. This is going to be nice for us because it's going to be introducing some randomization in the data. In fact, the vulnerability score itself, we have a separate project that I'm not going to talk about today. The VISP itself has been limited in use to make sure that actually now it aligns with a particular outcome and predicts some particular outcome that we want to track in matching people to resources. So, you know, I gave you a little bit the perspective of how the current system is working. There's a few concerns, though, about it. And in fact, LASA has been very concerned about it since our very first meeting, which resulted in them putting together this ad hoc committee on Black people experiencing homelessness, which basically looked at issues of race and equity in housing allocation and in homelessness in LA. And one of the findings was that, well, while 9% of people in LA are Black, 40% of people experiencing homelessness in LA are Black. So Black people are really disproportionately affected by homelessness. And they also found that Black people are more likely to return to homelessness. So let's say you give two people a resource, Black people are more likely to return to homelessness than their white counterparts. This is just one issue of equity I'm mentioning, but there's many more related to gender and so on. I'm going to use race in my presentation. So we've basically partnered with LASA, Los Angeles Homeless Services Authority, which is the entity in charge of matching people to resources in LA, and that manages basically those resources. And the question we set out to answer is, well, is there a way to use the resources that they have, the few resources that we have, more efficiently, and at the same time, can we make our policy more equitable in some sense or more fair in some sense? Okay. To this end, they shared some data with us, data from what is called the Homeless Management Information System, or HMIS for short. And what this is basically, it lists all the contacts individuals had with the system. So each time you encounter an individual, either during a street outreach or in a shelter, or each time they enter a resource, it lists that person's information, whether they received the survey, whether they were matched to a particular resource. And now from this, you can start building trajectories of what happens to people in the system, right? Are they coming back? And based on these trajectories, you can start defining outcomes that may be useful for like optimization purposes. For example, the outcome we're going to be working with is return to homelessness. So basically, after someone gets a resource, do they come back to the system or not? There's a few challenges with this data. There's a lot of challenges, but I'm going to just highlight one theoretical challenge here, which is the fact that this data is not collected using randomized trials, right? It's not that we put people randomly in resources. Instead, there was an underlying policy that was followed and that we don't know. That resulted in people getting matched to housing. And obviously then the challenge is that, well, we don't know what would have happened to an individual had they received a resource different than the one they actually got in the data. Why is this important for us? Well, because if we're going to design new policies that are different than the historical one, we need to be able to evaluate their performance. And so we're looking here at counterfactual performance of the policy. Yes.
To some extent, I think you can actually draw some causal inference.
Exactly.
Around the thresholds.
I'm going to tell you what I'm doing. So there's many things you can do. I'm going to propose one thing, but there's other things you can do under certain assumptions. Yeah. So this is going to be an observational data setting. All right. So so let's first formulate our problem mathematically. I'm going to begin by talking about our model. So in our system, right, there's individuals that arrive over time. I'm going to index them in this set calligraphic K. And in fact, I'm going to let this set go to infinity. So I'm going to really look at the long-term performance of my system. What's important here is that the individuals are going to be characterized by their covariates. In particular, for an individual indexed by K, I'm going to characterize their covariates by, denote their covariates by X sub K. So what this corresponds to would be, for example, their answers to the VI SPDAT, or their gender, their race, any information we have in the data. We had like hundreds of covariates in the data. What we're looking to do is to decide for each individual what kind of resource they should be matched to, right? So they are going to arrive in the system, and then with a certain probability, based on their covariates, they're going to be matched to either no services, treatment 0, rapid rehousing, treatment 1, or permanent supportive housing, treatment 2. Naturally, we can think about having many treatments. In general, I'm going to talk about the no treatment option as treatment 0. Treatment here, you should think about it as a resource, right? I'm talking causal inference lingo, but this is what really I'm referring to. And of course, we want everyone to be matched to a resource. Therefore, these probabilities should add up to 1. So the idea here is that someone comes in the system, I'm going to match them to a queue, then they're going to wait in that queue. Each time a new resource arrives, that resource is going to be matched to the first person waitlisted in the corresponding queue. And so when do I get a resource? I get a resource when all the queue in front of me has emptied and a new resource arrives. Right? This is kind of nice because this model is kind of nice because I know in advance which resource I'm going to get. Right? In the current system, there's people waiting. And they don't know if they will end up receiving something or not. With our approach here, you're guaranteed that you will get whatever you're waitlisted for. And as we'll see, in fact, this policy is not going to be randomized, but I'll get to that in a bit. The main challenge we have, right, is that those resources are finite, and we don't have many of them per person. Think of these as per person capacities. The only resource of which we have many is the services only. Here we're going to assume that B0 is infinite. Okay? And we're going to work with the potential outcomes framework of causal inference, where basically we're going to denote by Y sub K with the superscript the index of the resource or the treatment as the outcome under each resource for individual K. Okay? Of course, we don't know these quantities. For each person, we only know one of these quantities, the outcome under the treatment they received in the data. Okay? We're going to make the assumption here that the joint distribution of the covariates and the potential outcomes is for across individuals is IID. In other words, for all individuals coming from the same distribution. However, I don't know that distribution. I'm going to denote it by Q. Sorry. Moreover, because we don't have access to the potential outcomes, as we're going to see in our formulation, we'll be able to replace in our optimization problem these potential outcomes by their expectations. So basically, we're going to denote by F sub T of X the expected value of the potential outcome under treatment T for individuals with covariates X. Again, I don't know this quantity, but perhaps there is hope to estimate it from the data. So now we take the point of view that we don't know this distribution Q of the covariates and potential outcomes, but that we have access to historical data in the form of, for each individual I, their covariates, the treatment they received in the data, the resource they received in the data, and the outcome from receiving that resource. So YI here would be basically YI of TI, in other words, the potential outcome under the treatment that person received in the data. So what's our policy design problem? Where our objective is going to be to maximize the long-term expected outcomes of our policy. So pi here is my policy. Remember this probability of getting match to each of the resources. What I care is about the long-term performance. So we're taking the limit as the number of individuals in the system tends to infinity. And we're going to be interested in expected outcomes, right? For any given individual with covariance xk, this is the probability that they receive resource T, and this is their outcome under resource T. At the same time, we have capacity constraints that say that basically you cannot get matched to more resources than there are available, and think about BT here as the rate per person, okay? As I mentioned, right, the key problem in our work is related to fairness. Here, I'm going to just focus on the capacity constraints for most of my talk to streamline exposition and to avoid having huge amount of notation, but then I'll discuss how the same approach that we have can just be adapted to incorporate different kinds of fairness constraints.
Yeah. So how do you define exactly BT?
BT? Yeah, sure. So let's say there's only enough resources of RRH to allocate to 2 out of 100 people, then BT would be 2%.
It's the rate.
Yeah, it's the rate. Yeah. Yeah. So we can write our constraints in this form without the limit, just under our assumptions that we have IID distribution for the across individuals. Okay. And so this is our optimization formulation. This says I want to identify the policy pi that's going to maximize the expected outcomes on the population. Again, this is the same as taking the limit as the number of individuals, 10 to infinity, subject to meeting our capacity constraints on expectation. Now, some people may frown at this point. Phoebe, why are you meeting the constraints on expectation? It could be that you never meet them. You are right. However, you will see that we will propose an online policy that is always going to satisfy these constraints and that is going to be optimal in this problem. Therefore, we won't have issue of feasibility. Yes?
Are you assuming M is known or part of the problem is learning?
Good. We don't know M. Yeah. I don't know the distribution with which I'm evaluating expectation. I don't know M. Yeah. And my pi can be any arbitrary policy that maps the covariance X to the this distribution. Okay. All right. So this is challenging because we don't know the M, because we don't know that expectation. So what we have access to, though, is data. So the question is, can we use this data that we have to learn a policy pi that will be asymptotically optimal in this problem? So we're going to start by deriving a policy, and then we will show that that policy is actually optimal in the problem. So what we do, we intuitively, we're going to take the Lagrangian dual of our problem by associating with each of our constraints a dual variable mu t. We're going to relax the constraints in the objective, penalize violations of our constraints, and formulate our dual problem. Okay. So in this dual problem now, so here I've written it explicitly, and here I've done just some reshuffling. Let's look at this second expression here. Remember that my pi's, they should add up to 1 across the treatments, right? So for any fixed mu, what is the optimal pi here? It would be 1 for the treatment that has the highest value of this difference, right? And 0 otherwise. Okay, so for any fixed pi, we can write the corresponding optimal policy for the inner problem in this fashion. It's 1 if t achieves the maximum of this difference and 0 otherwise. We can break ties in different ways. Here we chose to break ties by just selecting t to have the smallest index. Okay. Now that we have this policy pi, we can just replace this summation that I had inside. We can get rid of the inner maximization problem and replace pi by its expression to get rid of the summation and instead identify this as the maximum across treatments of this difference for any given x, right? And I'm going to call the solution to this problem mu star, but you will say, but Phoebe, how do you compute mu star? You don't know the expectation here. That's fine. what we will do in a moment, I'll show it, but if I could compute that mu star, I could actually come up with a good candidate policy that would basically assign to the treatment that maximizes the difference where mu takes the value of mu star. Okay. What would the policy then look like in an online setting? Because right now my policy is not really online. In an online setting, what I would do is each time a person with covariance X arrives, I evaluate for each treatment the difference between M and mu star, right? I identify the treatment that has the greatest value and put that person in the corresponding queue, okay? So just based on their covariance. Of course, I don't know the mu star, but what I would do based on the process I described to you before, where people are just waitlisted for a resource, is I would only match them to a resource when that resource arrived. Therefore, by default, I would satisfy the capacity constraints I mentioned, okay? What we're able to show is that this dual price queuing policy is actually optimal in the original problem. We still have the issue that we cannot compute it, but if we could show that it would be optimal in the original problem. Okay. So now what's next? Yeah.
Being waitlisted doesn't mean that you will be satisfied.
Say that again.
Being waitlisted doesn't mean that you will be satisfied later on.
Well, you will be on. We will see that you will always be. Well, yeah, you will be in the infinite setting, right? In the infinite horizon, you will be served. Yeah. Right. So we only have observations now, like observational data, right? The covariates, the treatments, the outcomes under that treatment, and we cannot compute mu star. So what do we do? Well, what we're going to do is very simple. We're going to just replace in the original problem. So this was, if you remember, the dual problem in which I have plugged in my optimal policy pi. We're going to replace it with its sample analog, where basically the expectation is replaced with the average, and the M is replaced with an estimate of M that we're going to call M hat. Okay. Sorry, you have a question?
Oh, no, sorry.
Okay. And now this is something that I can solve if I have a good M hat. Yeah. Indeed, it can be reformulated as a finite LP, right, by just linearizing the objective function. What would our candidate sample-based policy then look like? It would look exactly like the one I derived earlier, with M replaced by M hat, with mu replaced by mu hat, and M replaced by M hat. And this again, this is something I can again compute. Okay. So what do? Each time a person comes into the system, we identify which treatment they should be matched to based on M hat and mu hat this time. Match them to the corresponding treatment, let them wait there until they are served. Okay, and we show that this policy has the same performance, is actually optimal, right, in the original problem under some assumptions for our M hat. Okay. So this is the theorem that I've made a little bit informal here that shows that the expected outcome of this sample-based, what we call dual price queuing policy, is asymptotically optimal in the original problem. Yeah.
I don't know if this is, I'm trying to phrase the question, but I'm surprised the policy doesn't consider, like, has a shared dual price as opposed to, like, considers how good another treatment would be for me in particular compared to anyone else.
Say that again,
so,
say
like,
that again.
If for me, like, you know, M hat for 2 is really high, but M hat for 1 is like that minus epsilon, it seems like you might want to give me 1 instead of 2, but this policy doesn't do that. Like, this policy would give me, like,
so the treatment 1 gives you some amount, and treatment 2 gives you some amount minus epsilon. Yeah.
And I guess it would do that because you're subtracting the shared dual.
Right.
I see, but
so it's basically it says I would match you to the treatment that's best for you, but I need to account for the cost this has for the entire system, which is done through the M hat, mu hat. Sorry. Yeah.
Okay, no, I think that makes sense.
All right. So far I just talked about capacity constraints, right? Budget constraints basically, or capacity constraints. But you know, my whole motivation was about fairness. it can be shown that everything that we've done here, you can do it in exactly the same way if you have fairness constraints. You would just treat them in the same way that we treated the capacity constraints, and all this would change is how I compute my pi, basically, right? What is the rule that I use in deciding which treatment I assign to you? We would have some additional dual variables for the additional constraint, but the story is very much the same. So what kind of constraints can we do? The first one, that's very natural one, and that's actually, you know, at LASA, they care a lot about when evaluating the system, is what we call statistical parity in assignments, just like statistical parity in like machine learning. It says that we want that the probability basically that you receive any given treatment should be similar no matter your race, for example, in this case, or so no matter which group you belong to. And this parameter delta, the right-hand side here, would control how much like unfairness we're willing to tolerate. An alternative that also policymakers care a lot about is statistical parity in outcomes, which says that no matter what group, what race, for example, you are, the probability that you have a positive outcome should be pretty much the same. And this is particularly important in the context of LASA or of like LA, because remember, rates of return to homelessness are far greater for Black individuals, so this would sort of mitigate this issue. So let me now move on to some numerical results on real data. So remember, from the HMIS data we got, we were able to build trajectories of individuals in the system. We had about 63,000 individuals with data from 2015 to 2019. For each individual, we had 162 covariates, which include their answers to the VISP DATs and other personal characteristics like prior housing history, race, disabilities, and so on. We broke this up into two parts, right? The training data until 2017, and then the test sets from 2018 onwards. We use the training data to learn treatment outcomes, to learn the budget, so the capacities, and to construct the policy. And we use the test set to evaluate performance. Something to note here is that when I say evaluate performance, because we're not deploying, we cannot really evaluate the true performance of our policies. So what we did is that for doing the counterfactual evaluation, we used the whole data. So both train and test to do the evaluation. This gives us basically more data and it's a little bit more robust in that sense. But to be fair, you would need to do an actual deployment, right, for true performance. So let me give you a little bit of detail on this data. We had 4 instead of 3 interventions because after speaking with matchers in LASA, we found out that the 2 types of PSH interventions were quite different in terms of how they work. So one is tenant-based and the other is project-based. The tenant-based being kind of PSH project-based being more similar to RRH. So those were the capacities. So what does this mean? So services only, I have as many as I want. There's only enough resources to serve about 11% of people with rapid rehousing, 2% of people with PSH tenant base, and 4% with PSH project base. So as you see, there's really very few resources to go around. What this means, unfortunately, is that there's only so much improvements you can do, but that also any improvement that you have is really important just because of scarcity, right? The outcome we're going to work with is having no return to homelessness within a 2-year window following the intervention. And we're going to look at 3 policies, or we're going to design rather 3 policies. One is one that's not necessarily fair, it's just the most efficient one. So kind of what I presented in my talk, right? And then we're going to look at allocation fairness, one that is like satisfies, that is fair in allocation by race, and then outcome fair, which is fair in outcomes by race. Yeah.
So could you remind us what is SO? What is that capacity?
Yeah, SO stands for services only. It means you don't get a housing resource, you receive only services that you may need. So it's really like no intervention case. Mm-hmm. In my plots, I'm not only going to show you 3 policies, I'm actually going to show you 4. On the left is going to be the historical one. So what happened historically, okay? So here I'm showing in these plots, each chunk of graphs is a different policy. On the y-axis, I'm showing the probability of receiving, in this case, PSH. And the policy I have circled is the one that I would expect to be the best in the sense that it satisfies those constraints. So here I've circled the, a policy that is fair in terms of allocation. What we did here is that we prioritized minority groups. So in my slides before, I kind of showed you, oh, you want the outcomes for both groups to be close. Because of our discussions with LASA, we decided to prioritize here groups that had been traditionally marginalized. So what we see, right, is in the historical policy, white people, which are shown in blue, have kind of higher outcomes than Hispanic, others, and somewhat close to Black or African Americans. And in this policy that prioritizes minority groups, white people receive fewer PSH resources. On the other hand, let's say you decided to optimize based on outcomes, the story would be different and you wouldn't have fairness in the allocation necessarily. Okay. Here I'm showing allocation fairness for rapid rehousing, so for a different type of resource. Here you will notice that the historical and the allocation resemble more to one another. The key message here is that if you went with a policy that just optimizes efficiency, you would really prioritize white individuals, which may be undesirable. What about outcome fairness? Well, we can see here that the historical allocation had somewhat better outcomes for Black people and for minority groups in general, but that we can increase overall outcomes by having a policy that is fair in terms of allocation, prioritizing minority groups. So this may be desirable. Yes?
When you're optimizing for outcomes, you see something like people with within each group, the people with the lowest risk score of that category get prioritized or something because they're more likely to have a better outcome.
Okay, very good. Yeah, so the short answer is we haven't looked at that, but this is an interesting question that I think touches upon the second part of my talk, and that's, I think we can discuss at that point if that's okay. Yeah, I think I will have time to go through it, but it's a very good question. Yeah. I can't hear you, sorry.
Can you say what an improved outcome would be?
Oh, so it's a no return to homelessness. So within 2 years. So you have basically fewer people returning to homelessness by using this policy than another one. Either one, Nikhil, go first. I think you are.
Is the 2 years after like the start of the intervention or the end of it?
The start of the intervention. Yeah. It's from the moment you are given the resource, because this is like a long-term thing. So if you get the resource, you can stay in it. If you don't come back in the system, we consider this to be a good outcome. Is this perfect? No, it's not perfect, because maybe people don't come back just because they're super upset with the system, right? So it's not perfect. It's the best we can do with this data. We have some collaborators that have been able to link this data with county data to have outcomes that relate to, health and like interactions with hospital services and stuff like that, that may be more meaningful. And you could, of course, apply this approach in that case. Yeah.
It's like housing, how long do people typically get housing?
Oh, good. So permanent supportive housing is unlimited duration. But you will find that some people still leave the housing resource for one reason or another. Rapid rehousing is in principle limited intervention, like 3 months, but you can stay longer. The idea is that the hope is that this is enough to support people such that they can find something else or be able to cover rent of staying still in that same resource.
It seems like all of the plots are Pareto improvements over historical.
Mm-hmm.
Do you think that's because like at the individual level, you're sort of doing the treatment effect calculations, so you're just better allocating individually as well? Is there something else?
So how do you know that it's like formally that it's Pareto improvement? I'm not sure. Yeah. Sure. Yeah, I think it's because you're optimizing a particular outcome. Honestly, like for me, I think it was a big surprise how well things are done. You know, yeah, certainly there's issues of equity and so on, which are harder to think about. But in terms of efficiency, I think this is actually not bad. And in fact, even in the in our other work on predicting vulnerability based on data, you find that actually the current vulnerability score is kind of not badly, not bad. It's not super well calibrated, but it's quite good at sorting people the right way, which is very interesting. I think it basically, you know, it's very encouraging that yeah, people on the ground really know what they're doing. But you can still get improvements from using AI systems, which is also something positive, of course. Yeah.
Are you going to talk about how you estimate them? So confused around how you get them.
Oh, sure. Yeah, sorry. Yeah, so very good question. So in all our experiments, we use like a bunch of machine learning models. What we do is we subset on the groups that receive that particular treatment, reweight based on everyone's probability of receiving that treatment, and use a machine learning model with like weighted, basically, classification, let's say, to predict the outcome. Yeah. So using IPW in some sense, yeah.
But you're not exploiting the threshold variation. Because I mean, the question I have was more about like regression discontinuity design. In some ways that go close to the threshold, some receive it, some don't receive it. And
good. So in the data, there was no clear use of the threshold. So there was a general sense so that you are more likely to receive the more supportive resources, the more vulnerable you are. But it wasn't just that people at the boundary were getting the resource. It could be that you scored very low and still received the resource. So yeah, the only thing that we noticed that was happening is that people with disabilities, that PSH were only going to people with disabilities. And so in our policies, we only allowed PSH to go to people with disabilities. So although this was not a formal rule, as far as I understand, it was kind of followed in the policy. And so how we did this is using propensity weighting to do that estimation. Like we learned the propensity score, the probability that you receive each treatment.
Score to receive the treatment.
Yeah, exactly.
And then, but for evaluation, you're not using IPS.
So for evaluation, we take the entire data, use the predicted outcomes based on the entire data rather than just the train or the test, and assume that this is the ground truth. Not perfect by any means. I think it's quite common way of doing things in causal inference where you don't have a way of deploying.
Another way would be to use like the probability weights, invert them, and then using the actual outcomes, you evaluate the policy.
Yeah, you're right. You could do it. Yeah. That seems similar, but you're right. You could do it in one shot. Yeah. All right. So now the question is, what happened to efficiency? So we saw we could become more fair and seemingly improve outcomes. So let's give some numbers here. The historical policy, as I said, is quite good. We have 60% of people exiting homelessness. If you had perfect foresight, so if you knew who exactly is going to come up in the system, you would have a 63.3% positive outcomes. Why can't you meet that? Well, you don't have perfect predictions of the new hats, and because you're using just the training data as opposed to both the training and testing, and you don't know, and there may be a shift in the data, right, between the training and testing phase, like just who shows up. There may be a shift in the budget. Many things can happen, right? So what can we do? In terms of the best that you can do from the data is 62.25%. These are evaluation results, right? What is interesting here is that actually having fairness constraints comes at basically zero price of fairness. So you can have a policy that's as good as the optimal one and have it be fair in a way that suits you. This results in thousands more people exiting homelessness. This may not seem like a lot, but I think it has a big impact. You know, keep in mind that we only have enough resources to cover about 16% of the population. So with not a lot to work with, I think these are very nice improvements. It's also more fair and equitable, and the price of fairness essentially is zero. Yes.
Yeah, I guess could you explain the foresight baseline a little bit more?
Yeah, sure. So in the perfect foresight is like if I knew exactly who's gonna show up, if I knew exactly the M hats, how would I allocate resources and what would be the outcomes and what would be the corresponding outcomes of that policy. So we use the test data in order to compute the policy here. It's like a matching where I know all the information. Does that help?
Yeah.
And if there was no distribution shift, if I had large amounts of data, our policy would exactly match the perfect foresight one. But because of these two things, you know, based on seasons, perhaps it changes who comes up in the system. Things happen in the economy, it changes who comes up in the system. So there is naturally a shift. In fact, we've did amazing work like trying to represent the shift in the distribution, and you can clearly see that people change. But you know, in spite of that, you can have improvements, which is nice. Yeah.
Just at the intuitive level, why do you think the price of fairness is almost there? Is it because like the population is homogeneous, or?
That's a good question. That's a good question. Like the best answer I can give you is that in many applied problems, the price of fairness is often close to zero. So that's all I can tell you empirically. Now, why this is true in general? Actually, I'm not sure. Nikhil, do you have a good?
My general answer to this is like there's just like so many people who are like sort of at the boundary that are basically equivalent on efficiency. You can play around on other dimensions.
Yeah. Yeah. Perhaps, yeah. All right. So there's a bit of a discussion here in terms of like practically applying this. So first of all, identifying which intervention, you know, like, so the question is like, how do you deploy this, right? Is it easy to deploy? Is it hard? It's based on like dual prices and whatnot. So my claim is that identifying which intervention to waitlist a new individual for is easy, right? Because all you need is having access to their information and knowing the function that maps their information to the MHAT. And you know the news, so you're fine. If you have an up-to-date waitlist of individuals that are available when a resource arrives, it's easy again to determine who should get the resource. It's just the first person to have arrived and that's waiting for that resource, right? So both these tasks can be done with a spreadsheet, which is nice. And, you know, keep in mind that our policies just provide recommendations. So, you know, an individual could just use this as a way of guiding, you know, who should I go talk to first rather than implementing this like hardcore in automated way. Something that our collaborators raised as questions in terms of deployment is the following. Well, what about the preferences? Okay. So here, I haven't talked about preferences. Preferences are not actually collected anywhere in the data, but in practice, it could be that, you know, the person I identify, actually, they don't want to live in that area, right? And I would argue that we can just apply our policy. What you do, you go to the first person, you ask them, would you like this resource? They say no, you go to the next and the next and next one. The performance of that policy, which takes into account preferences, is actually the same. Then they said, well, you know, what about document readiness? Like in practice, there's many resources that, you know, I may want to give the person the resource, but then I can't because I haven't like checked their documentation and everything. So our claim is, well, just consider people that are document ready. And in fact, ever since, since a couple of weeks ago, LASA has issued an announcement that says that they're only going to look at people who are document ready when matching people to resources. And the last one is, what if we cannot find the first person in the list? Again, you just go to the next person, next person, next person, unless you can find an individual. Okay, so in all cases, we simply assign to the next person in the queue for that resource. All right, now I have not much time, but I think it's interesting to discuss this, and this will perhaps help a little bit with what you're saying, what we were asking. So, you know, in all this stuff here, I assume that we have chosen a fairness constraint, or fairness in outcomes, or fairness in allocation, and we can optimize that, good. But in reality, it's not that clear, right? Like when LASA is looking at their system and when agencies look at their system, they look at different notions of fairness and like think, okay, am I happy with this? Am I happy with that? And so on. So here, we want to propose a framework for evaluating fairness of the current system and also helping agencies decide which fairness requirements they would like to impose when designing a new policy. Okay? And so my hope is that our framework can help a little bit guide this conversation. It's not an answer, but I think it can help guide the trade-offs that need to be made. So I'm going to be talking about stages of the allocation here. We have assessment, enrollment, allocation, and outcome. So you get assessed. This we have discussed extensively. Enrollment is typically when you are directed towards a resource, so you're recommended to receive PSH, for example, but maybe you don't receive it. What you receive is actually like dictated by the actual allocation, and the two may be different. They often are. And then we have the outcome. So these are the kind of steps in this whole allocation process. So we can, I'm going to go a little bit fast here. I'm going to use the same notation as before, and I'm just going to differentiate between the recommendation policy and the allocation policy. One of them I'm going to denote by pi, and the other one by mu. And I'm going to be working with a group G that's going to just be part of my vector of covariance X. Okay, first fairness notion, we saw it earlier. This is something I'm likely interested in, statistical parity in enrollments or in allocation. I'm going to focus here on allocation just for simplicity. This says no matter what your group is, you should have the same chance of receiving any one of the resources. Okay. This is nice, but obviously does not take into account risk. And certainly this is the issue now you were mentioning, that well, something that has statistical parity in allocation that LASA said they want, right? It does not necessarily align with prioritizing the most vulnerable, right? What you may then do is do conditional statistical parity in allocation, which says that condition, oh, Nikhil, I see you watching your time. Okay, should I wrap up?
I think you have 10, 12 minutes. Sorry.
Okay, sounds good. We had the questions in the middle,
yeah.
So, but I'm happy to stop with that. So something you may want to look at is conditional statistical parity in allocation, which says, well, I don't want people to have the same chance of receiving a resource independently of their group. I want to take into account risk, that perhaps people who have more risk may receive more supportive resources. And this is where this comes in. For example, we would like that if people are high risk, no matter what their race is, they should have the same chance of receiving any given resource. On the contrary, we are okay if they have different chances of receiving a resource than someone who is low risk. Okay. Something else that's interesting and that comes up to issues of equity in LA is this what we call equalized faithfulness in allocation. This says that no matter what your group is, the probability that you receive a resource different than the one you were enrolled in should be the same. This is important because there has been reports that in LA, Black people that, for example, get enrolled in permanent supportive housing may not be able to find a resource. And so in the end, although they're enrolled in PSH, they actually don't get it. So this is a measure of fairness we may be concerned with, okay? When we look at our system as a whole, and we may want to look then at ways of fixing it. So ideally, right, you'd like allocation and enrollment to match 100%, but if they don't, you may want that they don't match in the same way, independently of what group you belong to. Then we can look at similar notions in terms of the outcomes, that we want statistical parity in outcomes. This I talked about earlier. No matter what group you're from, you should have the same chance of a positive outcome, for example, of not returning to homelessness. You may say that part of the unfairness between groups may be justified by what risk they belong to, risk group they belong to. In this case, you may want to look at conditional statistical parity in outcomes. I believe less in this one because I believe that the goal of resource allocation is try to mitigate whatever may be going on with risk. But I guess this is, again, an ethical question to discuss. So what are our results here? So these definitions up to now, they're kind of variants of things we have seen in machine learning. So what I think is interesting here is like, okay, we have this framework that can help formally evaluate a given system, but also now what is the interplay between those fairness notions? So these are our main results. The first one is not unexpected. It says that statistical parity in allocation and statistical parity in outcomes are usually incompatible. So you cannot have both in the same system unless there's like something really exceptional that happens in your data. This is intuitive, but having this, I think, as a hard result is important because then you can go to the table with your collaborators and say, no, you really need to make a decision, right? Or you need to be willing to trade off a little bit of both. I'm not going to go through the details. The next question, which is back to what you were saying. Let's say now I use risk score to prioritize people. So what is kind of done currently in LA? Well, it turns out that if you prioritize by risk score, you will usually have unequal outcomes across groups. So, you know, the idea of prioritizing by risk score as a way of mitigating inequities actually is not true. And this is the case even if the score is a perfect predictor of bad outcomes. And the intuition is just because treatment effects matter. And treatment effects are not necessarily correlated with baseline risk. Sorry, I'm skipping all this in the interest of time. Now, okay, so now based on what I said, well, what if we include in addition to risk score, what if I include in addition treatment effects? Indeed, if I include treatment effects, I'll be able to have policies that are more fair in terms of their outcomes. So I don't only prioritize based on risk, but I also use treatment effects. Then indeed, I can have policies that are more fair. On the other hand, having policies that allocate based on risk and treatment effects may again not achieve full outcome parity. And if we use additional covariate information, we may be able to bridge some of that gap to have outcome parity. So in other words, you need treatment effect, you need risk, baseline risk, and you need covariate information. What is interesting here is why you need the covariate information. We find that actually only using among the covariates your group helps mitigate all the unfairness. So in other words, it's a bit the same message that you have in machine learning, that, you know, in order to have policies that are as fair as possible, you need to use, in addition to group, to risk score treatment effect, you need to use the group. Okay. So just to wrap up here, you know, there's this tension here between equality and equity, which we are all too familiar with. If we incorporate treatment effects in the allocation, in addition to risk, we have more flexibility to have better outcome fairness. Of course, there's challenges in terms of estimation from the data and so on. But incorporating group membership may actually further improve outcome fairness. And this, of course, now raises various ethical issues. You know, is it okay to use group to allocate housing? You know, is it worth doing if we can achieve outcome fairness and all that? And I think, you know, these results help frame a little bit the discussion around that and perhaps provide motivation to do it, recognizing though that there are risks in doing so, even if it yields outcome fairness.
Is your sense that in practice, you can imagine people don't like group membership and the optimization, but are fine in the prediction, or can people make that distinction in like where you're using group? Like you can imagine using it for the treatment effect.
Right. Good. Yeah. So this has been a question in the first part of the work that concerns us to some extent. So my policy my policy depends on M or on M hat. M hat, for this to be asymptotically optimal, may have to depend on group, because perhaps group is predictive of outcomes, and therefore my policy depends on group, as I've presented up to now. Is this okay or no? So on the one hand, you're right, you could use it just on M hat, right? But then have a policy that does not depend on M, and this is something that we can do using the tools I described. On the other hand, now you would have a price, right? Because you're not using group and therefore you cannot optimize your outcome as well. Yeah, now to your question, is it okay to use it on the prediction and not on the, is it easier to use it on the prediction in terms of application on the prescription? I think both are to some extent a concern. In the risk score work, for example, we are not using group status. Although it may be a predictor of your vulnerability. Again, I think it's worth looking at the price of not using group in both cases. Did I answer your question, Nikki? Okay, I'm gonna skip the summary because you got a good idea. I just want to say 2 words on the future work. These are 2 things that are keeping me up at night. I believe that we can achieve these improvements, but I do think at the same time that we have made some assumptions here that are worth investigating. So one is, well, we're working together with a team of social scientists. What this team is doing is they're rephrasing the way the questions are posed. If we change the way the questions are posed, this will change how people answer. For example, if I'm asked a highly personal question, right, I may be more comfortable replying it if you know, I know that person better, the question is phrased better, and so on and so forth. So this will basically change how data is collected, the distribution of our data, and in turn may impact the performance of our system. Just because, you know, in wanting to improve many things at once, we may make them worse, which we definitely don't want. And the second thing is, you know, we've assumed here that all the information that was used historically for matching people to resources was available to us. In other words, that I don't have an observed confounders. The reality is that matchers and social workers have information beyond what is listed in our data that they are using in order to decide on appropriate matching. And so this introduces basically an observed confounder. So is there a way to extend this work to cater for that setting? Nathan is not here, but you know, he would be interested in that. Yeah. So this is me. These are the papers. Yeah. Thanks, guys.